Okay, year 11, let's talk about how we predict entropy changes from chemical reactions and classify them as either increasing or decreasing in entropy. So, what have I written here? You can identify a chemical or physical change if, I can't even read. You can identify if a chemical or physical change increases or decreasing in entropy by accounting for the state changes in that reaction. Okay, reaction that is mainly solid and liquid on the reactant side and gaseous or a solution on the product side involves an entropy increase. A reaction that is mainly gaseous or solution on the reactant side and on the product side solid and liquid involves an entropy decrease. Okay, so we're looking at those and we're imagining those particle models and the differences in those and assigning whether the entropy is increased or decreased. If there's no change in state, what we're going to do is use the rules of, if there's no change in state, that's called a homogeneous reaction. We're going to use the number of particles on each side to use as an estimate. So the side with the greater number of particles will have the much more ways to arrange it, will have the larger entropy. Okay, so from there, we'll estimate if entropy increases or decreases, and we can use the symbology delta S for the change of entropy is greater than 0 for if it increases and is less than 0 if it decreases. So here I've got some examples. So number 1 is water is a liquid going to water as gas. Well, we know that a liquid is much more ordered than a gas. So going from a liquid to a gas is an increase in entropy. So delta S is greater than 0 because there's many more ways to arrange a gas than a liquid. Okay, all those spaces in between. Sodium chloride solid, I was going to say salt then, but solid, going to aqueous. Well, there's many more ways to arrange to dissolve salt in water than there are to arrange the sodium chloride into a solid matrix and then water. Okay, so entropy increases, delta S greater than 0. All right, what have we got? We've got dinitrogen dioxide, N2O2 gas, going to 2 molecules of nitrogen monoxide. Okay, here we can't use the change in state because gas going to gas, but we can count the number of molecules. So 1 mole on the left, 2 mole on the right. So we're increasing the number of molecules. Increasing the number of molecules increases the entropy because you can arrange 2 molecules in many more ways than you can arrange 1 molecule. Okay, so that one's also an entropy increase or delta S greater than 0. Okay, let's do a couple more, bit more complex together. So for the given reaction, state whether entropy increases or, not out, or decreases through the process and give a sign to delta S. Okay, is it positive, is it negative? We'll just write greater than 0 or less than 0. Okay, this first one we've got, first up, I'm not really concerned. First up, I'm just going to look at the states. Liquid, gas to solid. I don't need to count molecules at all because I can just go by the state. So the products is solids and we're starting, so low entropy, low disorder, very ordered. And a liquid and a gas can be very disordered, okay, many different ways. So this one, if it starts very disordered and goes to ordered, entropy is decreasing. Yeah, it's becoming more ordered. So delta S less than 0. Okay, it's becoming more ordered. Entropy is when it's becoming more disordered. Okay, here in the second one, gas, gas, gas. Okay, we've got a homogeneous reaction. Now I'm going to start counting molecules, okay? How many have I got on the left? I've got 1 nitrogen and 3 hydrogens, so that's 4 mole versus 2 moles of ammonia. So it's going from a less ordered, because there's many more ways you can arrange 4 things than 2 things. So delta S is less than 0 again. So we're becoming more ordered, okay? All right. Gas, 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 gas. homogeneous reaction. We're going to have to count molecules. Okay, we've got one of these things, which is actually ethanol, but you don't know that, and 3 oxygens, so that's 4 mole. And what do we got on the right? We've got 2 carbon dioxides and 3 waters. That's 5 mole. So the number of moles are increasing. There's many more ways you can arrange 5 moles rather than 4. So entropy change is greater than 0. So we've got an entropy increasing through that reaction. Okay, this fourth one, solid, 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 gas, gas. Okay. So all of the reactant side is solids, but some of the product side is gas. Okay. So gas is more disordered, so the reaction gets more disorderly as the products. So your change in entropy is greater than 0, or entropy is increasing, or your disorder is increasing. Okay, gas, gas, gas for this one. Homogeneous reaction, count the molecules. 2 molecules of carbon monoxide plus 1 of oxygen gives 3 moles on the left, and on the right we've got 2 moles. Okay, so many more ways that you can arrange 3 moles, so entropy is decreasing, so delta S is less than 0. It's becoming more ordered as the products. Okay, this sulfur one, solid, liquid, gas, gas. All the products are gas. Okay, so gases are much more entropy, so entropy is increasing over to the product side. So delta S is greater than 0. It's becoming more disordered. Gas, aqueous, aqueous, aqueous. Well, out of all of them, a gas is more disordered than an aqueous. So the left-hand side wins out here. So it starts more disordered than what it becomes. So entropy is decreased. Oh, help if I put the S in there, wouldn't it? Delta S is less than 0. Entropy is not increasing through that reaction, it's decreasing. Okay, aqueous, aqueous going to solid. Well, solid, less ways you can arrange it, so entropy is also decreasing through this reaction. It's becoming more ordered as a solid. Okay, we've got another example. Oh, we've got another couple of examples. The reaction below proceeds as written. Okay, what can you assume about the enthalpy of the reaction? This is a tough one, and I've seen this proceeds as written come up a couple of times. Okay, proceeds as written means it actually goes in this forward direction, and another word for that is spontaneous. So let's write that down. Proceeds as written. I'm going to write equals spontaneous. Okay, so we know from our knowledge of enthalpy and entropy that something is making this happen. Either it is increasing in entropy, it wants to become more disordered, or it is lowering it, or lowering its energy as well. So it's exothermic. Okay, and it might not be both of them, but it could be. But let's check. Okay, so we don't know about the enthalpy. We know that actually happens. We can assign entropy. What is happening with our entropy? We've got a liquid and a gas on the reactant side, and it's going to a solid. So it's becoming more ordered. So delta S is less than 0, becoming more ordered. So it's going against the entropic drive. Okay, the entropic drive wants it to become more disordered, but it's not. It's going against that. Now, the only thing that will make that happen and be spontaneous is that the enthalpy must be a very negative value. Okay, it must be really losing a lot of energy, and because that's what's making it happen. Okay, if it wasn't, it wouldn't happen at all, because entropy is saying no, I don't like this. If enthalpy as well was saying no by being endothermic, it wouldn't proceed as written. But the fact that it happens and it's going against the entropic drive is saying that the enthalpic drive overcomes the entropy less than 0, okay? So it must be exothermic, okay? It must be enthalpically driven. All right, example 3. Look at complete the table below, predicting whether a reaction will proceed as written, and I've written it there, or is spontaneous, okay? I like to say spontaneous rather than... Okay, so if you've got negative enthalpy, that's the enthalpic drive is there. That's how nature wants it. So tick, we've got this, or yes, okay? And here we've got entropy decreasing, so that's not what nature wants. So no, there's no entropic drive here. So is this reaction spontaneous? Well, we don't know. We haven't got enough information there. They're battling against each other, okay? So it depends if like in the last question, we didn't have an entropic drive, but it still went as proceeded because the enthalpic drive was still large enough, okay? But here we don't know how big they are, and we'll get to assigning numbers to these soon. Let's try the second row. We've got the enthalpy less than 0, so we've got an enthalpy drive. It's being exothermic. Nature likes that. Okay, and here we've got entropy increasing, so there is an entropic drive. So this type of reaction, where the enthalpy is negative, or it's exothermic, and the entropy is positive, or entropy increases, both the enthalpic drive and entropic drive are saying, yes, let's do this. So is the reaction spontaneous? Yes, always spontaneous. Okay, so for those conditions, you're always going to get a reaction that's occurring. All right, the third row, we've got the enthalpy being greater than 0. We've got an endothermic, so it's going against what nature likes for enthalpy. So there's no enthalpic drive, okay? Entropy is decreasing. That's not what entropy likes to do. It likes to increase, so there's no entropic drive. So neither enthalpy is pushing the reaction to happen or entropy. So is the reaction spontaneous? No, neither of them are pointing in the same direction. So it's a no, big no there. This reaction with these conditions for enthalpy and entropy, never spontaneous. Put them together, not going to happen. Okay, the fourth row, we've got the enthalpy going positive again. So that's not what nature likes. And we've got the entropy increasing though. So that's what nature likes, okay? But here we don't know for sure if the reaction's spontaneous. It depends which one's big enough for if it wins. So we don't know. We need some more information. Okay? And we'll get to that soon. All right. I think that's the last of the theory there. Let's pick up here in the next video.